one doesn't have anything. Hopefully it just works. Is it in okay. So techniques seem to be working. So thank you for the opportunity to come and speak here. I'm going to talk a little bit about how to make de novo design algorithms with smiles faster. So first I'm going to give an introduction and talk about a little bit about smiles and how we can generate them with deep learning and how we then use reinforcement learning on this and the program reinvent. And then I'm also going to give a little bit of background on smiles augmentation, how we can use data augmentation on smiles before coming to the main part of this talk, which is the new proposed way of doing the reinforcement learning in a double loop and look at some of the results and also some alternative strategies for increasing efficiency and compare to these. So this is an audience where I guess most of you know about smiles, but it's a sequence format for molecules, very handy to store in databases, exchange information. We have letters for atoms, brackets, and numbers for branching and long-range bonds. But we can also use it together with neural networks. We use a lot of language-inspired models. We use transformers or in the beginning, recurrent neural networks, where we can train a neural network to predict the next character in a smiles. So we give it a start token and ask it to predict the first one, and then given the first start token and the first token of the smiles, we can predict the second and so forth, and it can be trained very efficiently in batch mode. And that allows us, after training, to sample the probabilities distributions that are for the predicted next character token, and this works very well to generate new smiles. An interesting thing is that these neural networks then learn the distributions of the properties of the molecules that are generated. So in a way, we can take a database, say chemical, and then we can generate new chemical-like molecules that are hard to distinguish from chemical structures, but are not in chemical. So it's a way to do de novo design. And it turns out to be very efficient. In some tests, we have seen that we cover 95% of the theoretical space corresponding to a given data set. But just generating molecules may not be that interesting. We would maybe like to target the interesting molecules for our material science or drug discovery projects. So one of the ways that we do this is to use reinforcement learning. First, we train on a database of molecules. Depending on what kind of molecules you want, you will choose your database there. And then you have a generator, a prior generator generating chemical-like structures, and then you also copy this into an agent in a reinforcement learning loop that generates compounds, and we can score these compounds using a lot of external scoring functions, activity, toxicity, properties, synthesis, docking, etc. And then we update the agent depending on what score the molecules get. And during a couple of runs in this reinforcement learning loop, we start to generate compounds that score better and better and better in our compounded multi-parameter scoring function. So Reinvent is a tool that does that, and we use that at AstraZeneca, and it's open source, so we can also use it at Odyssey Therapeutics. If we look a little bit on what do we want from a de novo generative algorithm, one of the things is we want it to be resource efficient, so that we can find the molecules we want. We want it to be fast. We don't want it to do that with a lot of scoring function evaluations because it can be costly sometimes if you have a costly scoring function. It should also be optimization efficient, and what I mean here is it should be able to find well-scoring molecules that so fulfill these kind of multi-parameter optimization functions. We are also usually interested in the diversity of the output. We're not just interested in getting the single compounds because we are not there yet. We are rather interested in having a diverse selection of different chemical series that we can then work up with the orthogonal methods and in the standard computational chemistry workflows that we have to evaluate compounds, filter them, prioritize them, and get them synthesized. The algorithm should also be stable. It should be something that we can run and be reasonably assured that it will run the same time, same way the next time. There is a stochastic element in it, so different runs will produce different outputs, but at least we can maybe hope that we get the same kind of series out of it. And the same goes for reproducibility. When we run multiple times, we should get comparable results. But currently, it is working, but if you have expensive scoring functions, it can turn into a problem. So it could be interesting if we could do something to the resource efficiency. Some of the early works used hundreds of thousands of iterations and scorings of the molecules to achieve the goal. So I've been working with SMILES and deep learning with SMILES for a couple of years. And one of the things there is that we can do what we can call SMILES enumeration, but maybe we should call it SMILES augmentation. There are also other names used. But the key idea there is that a SMILE is just a view of the molecule. You can have several different SMILES forms of the same molecule. And if we use and present these different SMILES forms for the deep neural networks, it will learn better the idea about the molecule rather than the sequence of SMILES tokens. So that has improved SMILES-based deep learning QSAR, SMILES-based molecular generation, both conditional and unconditional. Deep representation learning can also be done via this augmentation. It has improved template-free reaction informatics models, unsupervised pre-training of transformer models, etc. So the idea is how can we then take this augmentation and put it into the reinforcement learning. So the solution there was to expand the standard single loop where we generate compounds, we score them, and we update the agent in batches. And instead, we have this inner loop where we generate some SMILES, we score them, as example with docking, which can take some time. And then we can reuse the SMILES. We can generate different SMILES forms. We can reuse the scores. We don't have to dock it again. It's the same molecule. It's just different SMILES, but then use the different SMILES forms to update the agent. So this inner loop is very fast. It's entirely RDK Python code. We take some SMILES, we create molecules, we create new SMILES from those, we reuse the scores, and then we update our neural network agent a couple of times before we get to the next batch where we generate SMILES. Then came out when I was working on this cool paper, also tackling the same problem. How can we achieve a higher efficiency in it so that we don't have to do tens of thousands or 50,000 iterations of docking before we get to a score. And this was an augmented hill climb. It's not the same augmentation as SMILES augmentation, but it refers to another augmentation in the scoring function. But the idea here is that instead of reinforcing the agent on all scores. We only take the best scoring compounds from each batch, and then the agent can learn faster because it sees the well-scoring molecules more than it sees the not so well-scoring molecules, where it is more drawn towards the prior. Yet another way to increase the efficiency is simply increasing the learning rate of the agent. We update the weight faster, and then we can increase how fast it learns there. So I'll return also to these and how it can be combined. So what I see here is some graphs to the right, where we see different number of augmentations in the inner loop, and we follows how many molecules have we been scoring and what is the average score in the top one in the batch. And we go from deep purple with only 1 SMILES per round, 1 augmentation per before we update the agent. And as we increase the number of augmentations, we see we don't need to score as many molecules, and we achieve much faster a high average score. But if we overdo it, 200 rounds in the inner loop before we go back, it actually starts to be detrimental. Then on the down, we see how many unique SMILES we found. And here, as this is an exploitation task, we almost immediately start to see that we found fewer SMILES. And this is linked to that we find the exact SMILES in much earlier. So for this task, if you want to exploit and find a single solution, around 5 to 10 augmentations seems to be optimal when you compare the speed with which you find a good score with the risk of overdoing it. Then another task here is more explorative. Rather than trying to find molecules similar to a single molecule, we try to find molecules that dock well into a receptor. And there can be many alternative suggestions for that, not just one. So here we're really exploring how many different kinds of molecules could you find that dock here. And here we also see an increased efficiency. We find much faster, higher docking scores. Interestingly enough, we also start to find a lot more unique SMILES. But if we overdo it again, we start to see a mode collapse, and we start to repeat the same kind of SMILES over and over again, and we're not interested in. And again, around 5 to 10 for this kind of computational budget seems to be a good way of balancing, updating the agent versus generating new SMILES to inform it. Then the first strategy for also increasing is simply to increase the learning rate, and this also makes us learn faster, but it also makes us affect other properties much earlier. Like if you increase the learning rate too much, you simply get an unstable learning, so that the validity of the output is simply gets wrong. So we see a large drop in valid SMILES in the beginning, but interestingly enough, the agent actually learns to generate valid SMILES under these conditions. We also see a drop in the number of SMILES found. We see a different picture for the similarity task. That's the number of SMILES found can be affected both ways. We can also combine the two, and they work synergistically. So if you increase the learning rate, you will need fewer augmentations to get the same speed up. but we can also very quickly start to come into a territory where we get simply caught in a local minima, and we never really reach the goal of finding the same molecule. Another thing we mentioned was the diversity, and this is usually something that is adversely affected. The faster we try to get to a solution, the less dissimilar solutions do we find. And we start to find the same smiles over and over again, and we overexploit that. But interestingly enough, if we do the augmentation, we actually start to increase the diversity here measured with internal diversity metric. So 5 to 10 augmentations in the inner loop actually increases the internal diversity in the novo design. Whereas for the learning rate increase, we also see an increase, but much later, and that is related to it starting to break down and creating what you could maybe call strange smiles. We also tried to look at how is the coverage of the chemical space, what kind of solutions do the different runs do. So we have some ChemCharts plots where we have mapped all the generated smiles into the same 2 dimensions via fingerprints and dimensionality reduction. And then we can follow how what kind of chemical space we sample. And interestingly enough, we see that between 2 to 5 inner augmentations, we stabilize the solutions. We start to sample the same areas of chemical space in different runs. So that is helping on the reproducibility of the system and the stability of the system. To the right, we compare the cosine similarities of the generated molecules, and we can see that we have these kind of similarities between augmentation 5 and 10, but augmentations of hundreds or a learning rate of 100 are clear outliers and not similar to the others. Now, when we generate compounds, we do it into an enormous chemical space. It has been estimated to astronomical numbers, how many different compounds that could be in drug-like chemical space. So the task of refinding known actives is a bit daunting because there could be so many solutions to it that we may need to sample for a very long time before we actually start to refine known actives. So we can also reformulate it into finding something that seems to be very similar to known actives. So smaller differences are not necessarily saying this is not the same molecule. So I did this comparison where we had a dopamine receptor docking targets, and then that was the only information we gave to the model. Okay, find something that docks well into this molecule. And then we had a lot of known actives in the system. And then we could compare what comes out of the generative algorithm. Can we find something in the known actives that looks similar? We could that. The standard reinvent found 2 compounds that were within a similarity of 0.8. Whereas if we increase and increase the number of augmentations in an inner loop to 5, we start to find 48 that is within this similarity threshold. Whereas the learning rate is more similar to the standard one and finds 2. And if we increase the similarity, if we decrease the similarity threshold, we start also to find more. This is a strong indication that we can't find relevant chemistry knowing only a target and don't have any ligand information. So returning to the other work, I mentioned about the augmented hill climb. We also thought about this. This could also be a valid proposition. So we wanted to test this out and also see, can we add the augmentation there also? Can we combine the two algorithms? So here we also had a dopamine QSAR model as a target, and we could do different runs of the augmentation, a double loop augmentation, or do an augmented hill climb, or just the augmented hill climb, and compare that to the standard reInvent 2.0. And what we saw was that augmentation increases both algorithms, but the major difference we found between the standard and augmented hill climb was the amount of really top scoring molecules that came out of the augmented hill climb. It was really good at finding molecules that scored in our QSAR model with a perfect score. So this was done by Rachel, who did a visit to us from King's College in London. So then we went and looked also again at the internal diversity, and we saw that the augmented hill climb decreases it a little bit, but the augmentations then recovers the internal diversity of the output. Interestingly, there was a difference between if you looked at the top scoring molecules, or you looked at the molecules that were slightly lower scored. So there was a different distribution. So depending on where you set the threshold for your score, you can get different amounts of internal diversity in your output. Yes. We also saw that there was a similar chemical space coverage between the standard one and the augmented hill climb. But when we add augmentation, we start to see a sampling of a different chemical space. So combining the two algorithms are definitely possible, and you can use it to increase the diversity of your output, while at the same time getting very many high-scoring molecules. Then there have already also been another way to increase this, which is experience replay, and I'll just talk a little bit about this. Because here you save the best scoring compounds in a kind of memory, and then each time you sample from this into the update of the agent. So that's yet another way of reusing the scores on. And it can also be used to seed the generation. If you have some known leads, you can already put them in the memory and present them to the agent during the update, and kind of guide it to the right area of chemical space you want to sample. So then there came also this cool paper where Jeff and Philip, they took this, and then they added the augmentation, double augmentation on top, and put it in overdrive. So it samples more than it samples more from the experience replay than it samples from the agent. And then they did a big benchmark that had also come out, testing the efficiency of the algorithm, how fast can we achieve good solutions in a lot of different benchmarks. So doing that, they saw that this combination of using the experience replay really aggressively combined with the double loop augmentation was really one of the fastest methods to achieve good scoring molecules in de novo generation. Yes, thanks. So in conclusion, I think even after 5 years, we can still find improvements for reInvent, retuning the various parts of the algorithms. This double loop augmentation, it seems like, had a beneficial approach on several aspects of the smiles-based generative design. It increases both efficiency and diversity at the same time. For explorative tasks, 10 times seems to be a good setting, and for a more explorative task, 5 times could be recommended. So a little bit of acknowledgement. I did this together with a couple of colleagues from Odyssey Therapeutics and also Rachel from King's College of London. So, and then also thanks to the attention and the audience and the opportunity to come here and present. So, thank you.
Other questions from the audience?
Yeah, especially kind of focusing on the further, I would say about the implementation of simulated cloud and policy of memory and other than in general, the problem of you make something identical moment. For example, if you use your embedding or different activity or something, can be more different now, identical molecule will be more different than more close now to the moment. That's something which like we can see that, for example, if you visualize your embeddings, like the same molecule with different now that they are close to the part. So it is more complicated.
The question is, if we do the SMILES augmentation or enumeration, do it then affect the embedding we see of the SMILES? Yeah. And this is maybe not related to this work, but we have used this effect where we used it for learned representations. So we made if you make an autoencoder from SMILES to SMILES, and you put in a different SMILES form, if you don't do anything about regularizing the Latin space, so to speak, you will end up in different places of the Latin space if you have a different SMILES form. But there you can actually regularize the entire neural network stack by showing a different enumerated SMILES, and then also generate different enumerated SMILES from a generator. And what you see then is that it gets very robust, so that different SMILES forms of the same molecule end up in the same place of Latin space. And at the same time, the Latin space increases its usability in example QSAR modeling. So it learns a more chemically relevant Latin space if you do that. I have seen SMILES enumeration be detrimental, and that was in reaction informatics, where you go from reactants to product or from products to reactants. There, if you just do the raw enumeration, it can be detrimental if you do too much, because you needed to learn something on top of it. And the answer there was to pick the possible SMILES that fits together. So if we take the Levenshtein distance between the reactant and the product, and the reactant and the product, and then pick the pairs that are similar there, you can still increase your data set size and get it to learn not only to use canonical SMILES, while at the same time it can work efficient in these string to string and sequence to sequence tasks. Yeah. Other questions?
There's some shorter ones in Discord that maybe you can take a look at before you have time.
Yes, I will take a look at the ones in Discord, and otherwise catch me. So thank you.